Solving simultaneous equations using elimination. So elimination is our second algebraic method for solving simultaneous equations, and again the aim is to create one equation with only one unknown in it. So we did that via substitution previously, and now we're going to use elimination, and essentially what we want to do is add or subtract the two equations in order to eliminate one of the variables, x or y. So I just want to touch on this idea of adding or subtracting two equations together just briefly. So if, for example, I told you that x was equal to 5 and y was equal to 8, then you would absolutely agree with me that if I added together the left-hand sides of these two equations, x plus y, that would have to be equal to the sum of the right-hand sides, 5 plus 8. So x plus y is equal to 13. Similarly, if I subtracted those two equations, so if I subtracted the left-hand sides, whether I did x minus y, which would give me 5 minus 8, so negative 3, or whether I did y minus x, which would give me 8 minus 5, so positive 3. But regardless of the operation that I perform, you can see that however I combine the left-hand sides of the equations, if I combine the right-hand sides in the same way, that still creates an equation, essentially a statement that is true. So we want to use this idea of adding or subtracting the equations when we're using the elimination method. Okay, so let's have a look at this first example. So we have two equations, two linear equations with two unknowns, x and y. In using elimination, we first need to work out which of the two variables we're going to be able to eliminate. And we'll be able to eliminate the variable for which we have the same term in each of the two equations. So in this case, we're going to be able to eliminate y because both equations have just one y. So our next decision, once we've decided which variable is to be eliminated, is to decide whether we're going to need to add or subtract these two equations in order to eliminate that variable. So the idea is if you have 2x in both the equations, if you subtract them, you won't have 2x, you won't have any x's anymore. Here we've got negative y and positive y. So subtracting these isn't going to eliminate y because negative y minus positive y is not 0. Similarly, even if we subtracted them the other way, positive y minus negative y is also not 0. But if we add negative y and positive y, that will eliminate the y's out of this equation. So as with our substitution method, and in fact I think it's more important in elimination, I'm going to number my two equations and I'm going to be clear in my mind about what I'm doing to combine them together. It's very easy for students to add together some terms and subtract other terms and lose track of what's going on. So in this case, I've got my two equations. I've decided I'm going to need to add these two equations together in order to eliminate y. So now we're going to add, and we're just going to add like terms. So we're going to add together 2x plus 5x, which gives me 7x, adding together negative y plus y, which is 0, that's why we chose to add, and adding together the right hand side, 1 plus 13, which is 14. And now we have a very simple equation with just one unknown that we can solve for x. Dividing by 7 tells us that x equals 2. And as with substitution, this is only half the solution. We know that the simultaneous solution is a point or an x and a y value that fit both equations. So we also need to find y, which means I'm going to need to substitute x equals 2 back into one of my equations. You can choose which one you prefer. So I'm going to substitute x equals 2 into, I'm going to go with equation 1, slightly smaller numbers. So 2 times 2 minus y is equal to 1. So 4 minus y equals 1, subtracting 4 from both sides and multiplying both sides by negative 1. So my simultaneous solution is x equals 2, y equals 3. So if you were to draw these two graphs, these lines would cross at the point 2, 3. Also just to note, we were asked to solve by elimination here, but this would also be a fairly straightforward problem to solve using substitution because it would be very easy to make x or y the subject here, y in particular, the subject in both of these equations. So for example, equation 1 you could rearrange to be, what's that going to be, y equals 2x minus 1, and therefore substitute 2x minus 1 for y in the second equation. So if you can make x or y the subject of an equation, substitution is still a perfectly valid method, but elimination actually quite often results in very simple equations quite quickly. You'll see here, adding these two equations straight away got us to the point that 7x equals 14. It's actually probably the most efficient method if the numbers work nicely for you. Okay, let's have a look at the second example. So two equations. Clearly here we're going to be able to eliminate y again. Both equations have 5y in them. Now the thing here is that both equations have negative 5y. So subtracting negative 5y minus negative 5y is going to give us 0. So we want to subtract 1 from 2 or 2 from 1. That's either will get you to the right answer. I'm going to do 1 minus 2 in order to keep the x term positive when I do the subtraction. So I'm going to do the larger one minus the smaller one. And you just need to make sure that you're consistent with how you do that subtraction. So 3x minus 2x leaves me with x. Negative 5y minus negative 5y is negative 5y plus 5y, which is 0, which is why we chose to subtract. And then negative 27 minus negative 23, so it's negative 27 plus 23, gives me negative 4. So now I need to substitute to find y. I'm going to go into equation 2, it's marginally smaller numbers. So we'll have 2 times negative 4 minus 5y equals negative 23. So that's negative 8 minus 5y equals negative 23. So rather than deal with all those negatives, everything here is negative. So if I multiply the whole equation by negative 1, 8 plus 5y equals 23. Subtracting 8 and dividing by 5. And so therefore x equals negative 4, y equals 3 is the solution to this pair of simultaneous equations. Okay, so the two examples we've done previously had obvious, it was obvious which variable we could eliminate because we immediately had the same term in both equations. Quite often you won't have the same term in both equations, but it's very easy to create the same term, remembering that we can multiply a whole equation by a constant, provided that we do the same thing to every term in the equation. So in this particular pair of equations, I don't have a like term. I don't have the same term. So 3x and x are not the same, and 2y and 7y are not the same. So I need to create that same term. The easiest way for me to do that in this case would be to make the second equation have a 3x here. So that would involve, in order to keep the second equation the same, multiplying everything in the second equation by 3. So I'm going to number my equations to start with. Then I'm going to be clear about what I'm doing. So I'm going to take equation 2 and I'm going to multiply it by 3, which gives me 3x plus 21y equals 15. Don't forget the right hand side, it's very easy to forget. I'm going to call this new equation equation 3. It's not technically a new equation, it's just another version of equation 2, but for the purposes of being clear about what we're doing, we'll call it equation 3. And I'm just going to rewrite equation 1 underneath, just so I can work with these two equations together. Okay, so now I've created this same term, 3x, in both equations. So now I need to decide, am I going to add or subtract? Clearly with one positive and one negative, adding them together is going to eliminate. So adding equation 3 plus equation 1, 3x plus negative 3x is 0. 21y plus negative 2y is 21y minus 2y, so 19y. And 15 plus 4 is 19. So y is equal to 1. And then we wish to substitute y back into one of the original equations. I'm going to go with equation 2 in this case. Okay, so x plus 7 times 1 is equal to 5. So that's x plus 7 is 5, so subtracting 7 from both sides, x equals negative 2. So therefore x equals negative 2, y equals 1 is the solution to this pair of simultaneous equations. Okay, so the last example here, it's clear that we don't have the same term in both equations, and we're going to need to multiply both equations by something in order to create the same term, because 3x and 7x, 3 and 7, one isn't a factor of the other. Similarly for 4 and 3. So we're going to need to multiply both equations by something in order to create the same term. So we have two options as to how we could do this. We could either do equation 1 times 7 and equation 2 times 3 to create 21x in both equations, or we could do equation 1 times 3 and equation 2 times 4 to create 12y in both equations. Now, it's much of a muchness here. Usually I'd say go with the smaller numbers. In this case though, if you use 3 and 7, you're multiplying the smaller equation by 7, so things aren't going to get super big. So it's really a case of, your personal preference. I might go with making 12y in both equations, so we'll go equation 1 multiplied by 3, which gives 9x minus 12y equals 9, and equation 2 multiplied by 4, so 28x minus 12y equals, so 4 26s, 4 20s are 80, and 4 6s are 24, so this will be 104. So now we've created 12y in both equations. I've got negative 12y in both equations, so I am going to need to subtract here in order to eliminate. I'm going to renumber these as equations 3 and 4. And obviously it makes sense to subtract equation 3 from equation 4 because the numbers in equation 4 are much bigger. So 28x minus 9x gives us 19x. Negative 12y minus negative 12y is 0, which is the aim. And 104 minus 9 is 95. So x is going to be 95 divided by 19. Now you can think about that in a couple of ways. Obviously 20 times 5 is 100, so 19 times 5 is 95. Also you could think about, 10 times 5 is 50 and 9 times 5 is 45, so whichever way you think about it, 5 times 19 is 95, which means that 95 divided by 19 is 5. Now we need to find the y value, so substitute x equals 5 into equation 1, seems the more obvious choice here. So, my apologies. So 3 times 5 multiplied by, subtract 4y equals 3. So that's 15 minus 4y equals 3. So negative 4y equals negative 12, which means that y equals 3. So therefore x equals 5, y equals 3 is the solution to this pair of simultaneous equations. Now we've had 4 nice examples which has given us nice whole number solutions. Obviously it would be perfectly feasible to get fractional solutions to your equations, but it doesn't change the process in any way, just makes the number work a little bit more complicated.